So in this section, we've learned how to express a function as a power series. And we also learned how to prove that the function equals to its Taylor series by evaluating the limit of the remainder and prove that it equals to 0. For the following 4 lectures, we are going to look at 3 methods to find the Taylor series and Maclaurin series of a function. Let's start with the first method, the direct computation. We've already used this method to find the Maclaurin series of an exponential function in lecture 32. So this method is to find a pattern of the derivatives so we can write out a general expression for the coefficients. In this lecture, we are going to look at 4 more examples using the direct computation method. So here's the first example. Find the Maclaurin series for sine of x and prove it represents sine of x for all x. So similarly to the exponential function, let's write out the first few derivatives and let's see if we can find a pattern. The function f of x is sine of x. And since we want to find its Maclaurin series, that is, we want to find the Taylor series at a equals to 0. So let's also evaluate f of 0. Sine of 0 equals to 0. Then, let's find the first derivative. Derivative of sine function is cosine function. And the first derivative evaluated at 0, cosine of 0 equals to 1. And the second derivative, so the derivative of cosine of x, that is negative of sine of x. And negative of sine of x at 0, the second derivative evaluated at 0 also equals to 0. How about the third derivative? Derivative of negative of sine of x, that would be negative of cosine of x. So the third derivative evaluated at 0 is negative 1. And how about the fourth derivative? So the derivative of negative of cosine of x, that equals to sine of x. And now we are back to the original function, f of x. So the fourth derivative evaluated at 0 equals to 0. So we can note that the derivatives repeat in a cycle of 4. Now let's write out the Maclaurin series using the derivatives evaluated at 0 that we just found. The first few terms are f of 0 plus first derivative at 0 divided by 1 factorial, then times x plus the second derivative evaluated at 0 divided by 2 factorial, then times x squared, plus the third derivative evaluated at 0, then divided by 3 factorial, then times x cubed, and so on. Now let's substitute the derivative we found in this Maclaurin series. So we found that the even derivatives evaluated at 0 are 0. So the first term, f of 0, is 0. The second term, first derivative equals to 1. So we have 1 divided by 1 factorial times x. And the second derivative evaluated at 0 is also 0. So the term with x squared vanishes. How about the term with x cubed? The third derivative evaluated at 0 equals to negative 1. So we have negative x cubed divided by 3 factorial. So now we can see a pattern. The terms with even exponents all vanish. So the next non-zero term would be plus x to the power of 5 divided by 5 factorial. Then minus x to the power of 7 divided by 7 factorial. And so on. We can also rewrite that in sigma notation. So this equals the sum for n starting from 0. We see that the terms alternate the sign, so we have the negative 1 to the power of n. So the first term, when n equals to 0, the sign is positive. Then we have x to the power of some exponent. For the first term, when n equals to 0, exponent is 1. For the second term, when n equals to 1, the exponent is 3. And the next one is 5, and the next one is 7. So we always add 2. when n increases by 1. So the exponent is 2n plus 1. Similarly to the denominator, it is the exponent factorial, which is 2n plus 1 factorial. And you can also check with the ratio test, the radius of convergence for this series is infinity. Then the next step is to verify that the function sin of x equals to this Maclaurin series. Then we need to use the Taylor's inequality. We notice that all the derivatives, the n plus 1 derivative, it will be either plus or minus sin of x or plus or minus cosine of x. And for these four functions, they are all bounded above by 1. So we can choose the n, the absolute of the n plus 1 derivative is always smaller than or equals to 1. And that is true for all x. So we can choose the upper bound, n equals to 1, in the Taylor's inequality. So the absolute of the remainder, Rn. By the Taylor's inequality, it is always smaller than or equals to n divided by n plus 1 factorial, then times absolute of x to the power of n plus 1. And we chose m equals to 1, so this equals to absolute of x to the power of n plus 1 divided by n plus 1 factorial. Now let's take the limit on both sides. So the limit as n approaches to infinity of the absolute of the remainder, Rn, it will be smaller than or equals to the limit as n approaches to infinity of the absolute of x to the power of n plus 1 divided by n plus 1 factorial. And by the growth rate, this limit equals to 0. And the limit of the absolute of the remainder has to be smaller than or equals to 0. So by the squeeze theorem, the limit of the remainder is 0. So we just proved that sin of x has a power series representation, and it equals to this Maclaurin series for all x. So far, we've only looked at examples of finding Maclaurin series of a function. Now in this example, let's find the Taylor expansion centered at a different a. Let's represent the same function, sin of x, but as a sum of its Taylor series centered at x equals to pi over 3. The steps are the same, so we are going to find the first derivatives, and let's see if we can find a pattern. Same as in the first example, we had f of x equals to sin of x. The first derivative, f prime, is cosine of x, and the second derivative is negative of sin of x, and the third derivative is negative of cosine of x. And we know that the pattern of the derivatives will repeat in cycle of 4. Now let's find the derivatives evaluated at x equals to pi over 3. So for the original function, f of pi over 3. Sine of pi over 3 equals to square root of 3 divided by 2. And for the first derivative evaluated at pi over 3, that is cosine of pi over 3, that equals to 1 over 2. And for the second derivative at pi over 3, that is negative of sine of pi over 3, which is negative of square root of 3 divided by 2. And the last one, the third derivative evaluated at pi over 3, that is negative of cosine of pi over 3, which equals to negative of 1 over 2. Now using these derivatives, let's write out the Taylor series. Let's write out the first few terms. We have f of pi over 3, then plus first derivative evaluated at pi over 3 divided by 1 factorial, then times x minus a, and a is pi over 3 to the power of 1. Then plus the second derivative evaluated at pi over 3 divided by 2 factorial, then times x minus pi over 3 squared. And let's write out one more term. So the third derivative evaluated at pi over 3 divided by 3 factorial times x minus pi over 3 to the power of 3, and so on. Now let's substitute the values we found when we evaluated the function and its derivative at pi over 3. The first term would be square root of 3 divided by 2, then plus 1 over 2 times 1 factorial, then times x minus pi over 3, then minus the second derivative at a is negative of square root of 3 divided by 2. So minus square root of 3 divided by 2 times 2 factorial, then x minus pi over 3 squared. Then the third derivative is negative of 1 over 2. So minus 1 over 2 times 3 factorial, then times x minus pi over 3 cubed. Then in repeat. Now let's write the Taylor series using a sigma notation. It will be easier to use two sigma notation, one for the even powers and the other for the odd powers. So this equals, for the even powers, we see that they will alternate the sign. The first one, when the exponent is 0, we have positive, and this, when the exponent is 2, we have negative. So the next one, when we have power of 4, it will have a positive sign. And we notice that in front, there's always a constant, square root of 3 divided by 2. In the denominator, here we have 0 factorial. Here we have 2 factorial. So the next one will have 4 factorial. And the exponent is 0, 2, next one will be 4. So using a sigma notation, it would be the sum for n starting from 0 of negative 1 to the power of n, since the sign alternate. Then we have the constant, square root of 3 divided by 2. Then we have the factorial of the even numbers, so 2n. Then times x minus a, which is pi over 3, then to the power of even numbers, so 2n. Now let's focus on the odd powers. We notice that the sign also alternate. So this term, it has a positive sign. The next term, when the power is 3, we have a negative sign. So for the next odd terms, which is to the power of 5, it will have a positive sign. So the sign also alternate. And the constant in front in this case is the 1 over 2. In the denominator, here we have 1 factorial. This term has 3 factorial. So the next term, for the fifth power, we will have 5 factorial. Now let's summarize that using a sigma notation. So we have a sum for n starting from 0 of negative 1 to the power of n. And the constant is 1 over 2. Then multiply that by the factorial of even numbers. So 2n plus 1 factorial. Then times x minus a to the power of odd numbers, 2n plus 1. So this is the Taylor series for sine of x centered at x equals to pi over 3. You can also use the Taylor's inequality to show that the function equals to this Taylor series. And here's the third example. Let's find the Maclaurin series for function 1 plus x to the power of k, where k is any real number. So similarly to the sine function and the exponential function, we are going to write out the first derivatives, and let's see if we can find a pattern to the derivatives. So the function here, f of x, is 1 plus x to the power of k. And since we want to find the Maclaurin series, so we plug in the number x equals to 0 to the function f of 0. And we get 1 to the power of k, which is 1. How about its first derivative, f prime? We use the power rule, we get k times 1 plus x to the power of k minus 1. And if we substitute x equals to 0, we get k. Then, the second derivative. So we bring the exponent in front again. We get k times the exponent, k minus 1, then times 1 plus x to the power of k minus 2. And if we substitute 0, the second derivative at 0, we get k times k minus 1. Let's do one more derivative, the third derivative. So we bring the exponent down, we get k times k minus 1 times the exponent k minus 2. Then times 1 plus x to the power of k minus 3. Then we substitute 0. The third derivative at 0 is k times k minus 1 times k minus 2. Now we start to get to the pattern. So let's write out a general form for the nth derivative. We see that every time when we take a derivative, we always multiply the exponent from the previous derivative. So if we have nth derivative, then we get k times k minus 1 times k minus 2 until we get to k minus n plus 1. And the exponent to 1 plus x is now k minus n. So if we substitute 0 to the nth derivative, we will get the constants in front, which is k times k minus 1 until k minus n plus 1. Now using the patterns we found, let's write out the Maclaurin series for the function. The general form for Maclaurin series is the sum for n starting from 0 of the nth derivative evaluated at 0 divided by n factorial, then times x to the power of n. So using the pattern we found, it equals the sum for n starting from 0. The nth derivative evaluated at 0 is k times k minus 1 times k minus 2 until k minus n plus 1. And we divide this by n factorial. Then times x to the power of n. If you have taken some probability courses or data management courses, you may notice that the coefficient in front, this term, looks very similar. We can also rewrite that as k factorial divided by n factorial times k minus n factorial. Or using the combinations, it is k choose n. And we also call this the binomial coefficient. So this is the Taylor series for the function. Now let's find the radius of convergence for this series. Here we have a combination of factorials. So let's use the ratio test again. Let's first write out the absolute of the ratio, an plus 1 over an, which equals the absolute of k times k minus 1 until k minus n plus 1 times k minus n. Then we have x to the power of n plus 1, then divide this by n plus 1 factorial. then multiplied by 1 over an. 1 over an is n factorial divided by k times k minus 1 until k minus n plus 1, then times x to the power of n. We can notice that these terms can cancel out with this term. And n factorial divided by n plus 1 factorial also equals to 1 over n plus 1. So this equals absolute of k minus n divided by n plus 1, then times absolute of x. Then let's take the limit of this ratio. The limit as n approaches to infinity of absolute of an plus 1 divided by an, which is the limit as n approaches to infinity of absolute of k minus n divided by n plus 1, then times absolute of x. We can factor out the highest degree, so limit as n approaches to infinity of n times the absolute of k divided by n minus 1, and divide this by n times 1 plus 1 over n. Then the n cancel out. Furthermore, this term and this term go to 0 as n approaches to infinity. And we still have the absolute of x. So as n approaches to infinity, this limit equals to absolute of x, and by the ratio test, the limit has to be smaller than 1 in order to have a convergent series. Thus, by the ratio test, the binomial series converges if the absolute of x is smaller than 1 and diverges if absolute of x is greater than 1. It is also possible to prove that the limit of the remainder approaches to 0 as n approaches to infinity, but that turns out to be quite difficult. So we are not going to prove that the function equals to its Taylor series here. So just a quick summary. In this example, we found that the binomial series converges to the function 1 plus x to the power of k. And the binomial series is the sum of the combinations k choose n times x to the power of n. Now let's look at one last example for this lecture. Let's find the Maclaurin series for the function 1 over square root of 4 minus x and its radius of convergence. We can actually rewrite this function as the function in example 3, 1 over square root of 4 minus x also equals to 4 minus x to the power of negative half. And I can factor out the 4 to the power of negative half so that the first term in the bracket equals to 1. 4 to the power of negative half also equals to 1 over 2. So 1 over 2 times 1 minus x divided by 4. And this to the power of negative half. So now we rewrite the function that looks similar to the function in example 3. If we compare this to 1 plus x to the power of k, we see that the exponent k is negative half, and we replace the x by negative x divided by 4. So, this function, 1 over square root of 4 minus x, we can rewrite that as a power series. We have the constant in front, 1 over 2, then the sum for n starting from 0 of k choose n with k equals to negative half, then times negative of x divided by 4 to the power of n. Or you can also expand the series. If you write out all the terms, you'll get to this form. And remember from example 3, the binomial series converges when the absolute of x is smaller than 1. But in this example, we replace the x by negative of x divided by 4. So this series converges when the absolute of negative x divided by 4 is smaller than 1, which also means when the absolute of x is smaller than 4. So, the radius of convergence, r, equals to 4. And that is the end of the first method, the direct computation. In the next lecture, let's look at the second method, which is term-by-term differentiation or integration.